tout le monde au séminaire en informatique qui sont axés cette année sur ChatGPT et les LLM. Notre invité aujourd'hui est Melanie MITCHELL de l'Institut de Santa Fe, qui est professeure là. Et ses recherches sont sur l'abstraction conceptuelle et la création d'analogies de toute façon. Elle a écrit un livre en 2009 qui a gagné le prix Phi Beta Kappa Science Book Award, A Guided Tour, A Complexity, A Guided Tour, puis un autre livre en 2019, Artificial Intelligence, A Guide for Thinking Humans, qui était finaliste pour le Cosmos 2023, prix de rédaction scientifique. Son titre est en français, et un instant où je l'ai mis, ici. Le débat sur la compréhension et les modèles LLM de l'intelligence artificielle. Si l'on peut dire que le grand modèle linguistique préentraîné comprenne et le langage et les situations physiques et les sociales qu'ils codent, est-ce qu'ils comprennent ça? Mélanie décrira les arguments pour et contre et elle discutera des méthodes pour évaluer équitablement la compréhension et l'intelligence des systèmes d'intelligence artificielle. Elle conclura par les questions pour les sciences plus larges de l'intelligence. What do you mean by wider sciences plus larges de l'intelligence? You mean all of cognitive science or even further?
Intelligence writ large.
Large, I like it. Okay. So everyone else knows that Melanie is a professor at Santa Fe Institute, and she's done a lot of stuff and written a lot of books. And now she's going to tell us what her take on the entry on the stage of this odd little character, ChatGPT, that we spend some of our daily time with. Melanie, welcome.
Thanks so much. And thanks so much, Stephen, for inviting me. I'll share my screen. Okay, and please feel free to ask questions during the talk. I'm happy to answer, have discussion during the talk, trying to figure out how to. Okay, good. So I'm going to be talking about this paper, this article that I wrote recently with my colleague David Krakauer here at Santa Fe Institute that was published in PNAS about this pretty interesting and really quite heated debate that is going on in the AI and cognitive science community about understanding in AI systems and particularly large language models. So we can ask, do current AI systems understand the data they process? This is a hard question to answer because we don't have a rigorous definition of understanding. And that makes it kind of us relying on our intuitions about what understanding means. But we certainly can say that in the past, AI systems certainly didn't appear to understand in any human-like sense data that they processed. And it actually matters quite a lot because it affects their ability to communicate with us, their ability to be robust in new situations that are different from their training data, and more generally, our ability to trust them. So I think we've all seen lots of failures of understanding in AI systems in the past. Here's some examples. I love this example from 2018, with a deep neural network that was trained on ImageNet and was able to identify objects like school buses with 100% confidence. But this group showed that if you do some kind of transformation, like a rotation or some other change in the pose of the object, that now the deep neural network was almost 100% confident this was a garbage truck, a punching bag, and here a snowplow. So obviously these neural networks that were trained on corpuses like ImageNet learned to identify objects very well, but were not really using the same kinds of robust features of the world that we humans use. And this can have lots of real world implications for systems that use computer vision in the real world, such as we've seen many times, Tesla cars going on autopilot, crashing into stopped emergency vehicles on highways because they don't recognize them as objects in the scene. And everybody here, I'm sure, has seen this kind of example of adversarial attack on computer vision systems, but just by putting stickers arrayed in certain positions on stop sign. The vision system can be fooled into thinking this is a speed limit 80 sign, not a good thing, obviously, for safety. And this is at different distances and angles from the camera. You can see that in most cases, the attack was successful. The lack of understanding also is shown up in ways that sort of address common sense understanding of the world. So here's an example of a self-driving car vision system correctly classifying these as cars and correctly, in some sense, classifying these pictures of bicycles on the back of a van as bicycles and people, but really not distinguishing between something that is actually in the real world that the car is looking at and something that's in an ad. And a similar error of understanding was shown by this Twitter user who posted that his Tesla autopilot kept slamming on the brakes in this area. There was no stop sign until he noticed this billboard, which has a sheriff holding a stop sign in some kind of advertisement and within huge letters, stop. But clearly any human driving would not think that that was an imperative to stop, to slam on the brakes right in front of that billboard. They know the context, they understand that in this case, it's not a stop sign that you should stop for, but the car, it hasn't seen this kind of thing in its training data, and it's not able to understand this particular context. In other cases, many people have identified what are called shortcuts in machine learning systems. For example, this paper, these researchers were applying deep neural networks to classify skin cancer in photographs like this. And they pointed out that in their training set, because of anomalies in the training set, the deep neural network first learned to identify rulers in the picture as a good cue to diagnose skin cancer, because the photos with tumors, so skin cancer, malignant skin cancer had these rulers in it. So the ruler was being used as obviously a shortcut statistical correlation, but not something that any human trying to identify skin cancer would use. This is a particularly striking example of this kind of shortcut, but more subtle shortcuts appear in many machine learning benchmarks that systems are able to classify images or answer questions based on shortcuts rather than on actual features that are relevant to the underlying question. Here's an example of a misunderstanding by Google Translate. This was something I tried just a couple of weeks ago, where I said, translate, the legislator accidentally left a copy of the important bill he was writing in the taxi, and it translated bill to facture in French. You all will know more than I that this is not really the correct translation of a legislative bill, but is something more like an invoice. So, but now, we have a new character on the stage of AI, large language models, and many people have claimed that these systems now have achieved a richer human-like understanding than previous AI systems. And indeed, you can ask ChatGPT to translate this sentence into French, and it translates the word bill into projet de loi, which is the correct translation. And you can even ask it, how did you know how to translate the word bill? It has several possible meanings. And it will tell you in great detail. It's been trained, et cetera, and based on the context of the sentence, which mentions a legislator and a document, it's clear that the word bill refers to legal document. If the context were different, such as referring to a payment or a bird's beak, the translation would be different accordingly. So yeah, this sure looks like something that is really understanding this sentence. And Terry Sinofsky wrote an article about large language models in which he said, well, they're not human, but they're superhuman in some ways. And some aspects of their behavior appear to be intelligent, and I would add, and to understand. But if it's not human intelligence, what is the nature of their intelligence? And really, this is the question that many people in AI are really struggling with, to say what is exactly the nature of their intelligence. And this really matters because it gets to the question of, what's going to happen with these systems in the future as they're scaled up, and how much can we really trust them, or, if you like, fear them. So some people on one side of the debate, I'd say, are making claims like these systems are starting to become conscious. So this is Blaise Aguirre-Yarkis from Google, wrote about this in The Economist. Alex Dimakis, who's a prominent machine learning researcher, posted on Twitter that he's now convinced that scale is going to get us to general intelligence. That is, just convert everything to tokens and predicts the next token and do it at a very large scale, and we'll get there. And Chris Manning, head of the AI lab at Stanford, wrote that he thinks there's a sense of optimism that we're starting to see the emergence of these, what he called knowledge-imbued systems that have a degree of general intelligence, and I think implicitly understanding. So that's sort of one side of this debate. But other people disagree vehemently. For example, Jake Browning and Yann LeCun wrote that a system trained on language alone will never approximate human intelligence, even if trained from now until the heat death of the universe. And Alison Gopnik, a developmental psychologist at Berkeley, went a little bit further, I think, which saying that these models are not intelligent nor dumb. They're these words, intelligence, agency, and I think she would include understanding, are the wrong categories for talking about them. So how do we resolve these polar opposite views? Well, one group of researchers surveyed people in natural language processing, people who had published at prominent NLP conferences, and asked them, do they agree or disagree? Some generative models trained only on text, given enough data and computational resources, could understand natural language in some non-trivial sense. Agree or disagree? And really, the results were just split 50-50 down the middle. So you can see, people who strongly agree, weakly disagree. It's almost symmetric. So there's not a consensus on this at all, even for not just for current systems, but even for future systems that are given enough data and computational resources trained only on text. So I wrote a column recently in Science magazine called "How Do We Know How Smart AI Systems Are?" talking about how tricky it is to evaluate intelligence or understanding in these systems. And people have approached this in many different ways. The simplest way is just look at their behavior, like the Turing test, kind of idea. Let's just see, do they seem intelligent? Do they seem like they can understand like people? And I showed you that little dialogue I had with ChatGPT about translation. of a sentence, and it sure seemed like it was understanding. It gave me that impression. But of course, we have the problem of the ELIZA effect, which is that systems that communicate with us in language, particularly, and are articulate, we project onto them understanding. That's just the way that human psychology is. We tend to take what Dennett called the intentional stance. We believe that these systems have these qualities, but it may be an illusion based more on us than on the machines themselves. So a lot of people, of course, have tried to do something more objective to develop natural language understanding benchmarks and test systems on them compared to humans. But of course, I mentioned that benchmarks often allow shortcuts. So let's look at the general language understanding evaluation, which is a widely used collection of tests, natural language understanding tests that are given to systems, and its successor, superglue, which is even more challenging. And here is the leaderboard for superglue, which is this is sort of a average score on a whole bunch of different benchmarks. And here at the bottom are humans, human baselines, and above that are all large language models. So does this mean that large language models have exceeded humans on general language understanding, as is in the name of the benchmark? Well, no, of course not, because it turns out that even though it's named general language understanding, the actual benchmarks do allow for many kinds of shortcuts. That is, getting the answer right without having the underlying understanding ability. So lots of people have written about shortcut learning or various annotation artifacts in the data sets that allow shortcut learning, and have even made the analogy with clever Hans, to calling these systems clever Hans predictors. And of course, clever Hans was a horse who in the early 1900s was claimed to be able to do arithmetic and would tap its hoof in order to give the answer to an arithmetic question that was posed to it. But after much investigation, it was uncovered that the horse was responding to very subtle body language cues from its trainer rather than actually doing arithmetic. And the trainer, I think, was not even aware that they were giving those cues. And analogously, it's possible that, we have these benchmarks for understanding language that contain very subtle statistical associations between keywords, different phrasings, and so on, that give the kinds of cues that can be picked up by huge statistics-based systems. More recently, of course, people have been giving large language models standardized tests. We see that ChatGPT has passed the bar exam, medical licensing exam, and so on. But there we have possibilities again of data contamination. That is the problem that these systems have seen these exact questions or ones that are quite similar in their training data, but also that because of this phenomenon of shortcut learning, it may be that, and problems with the tests themselves, it may be that performance on these tests might not correlate with performance in the real world. We see headlines like ChatGPT gets an MBA, that it did better than a lot of students on a Wharton management school business exam. It might be smart enough to graduate law school because it passed law school tests, and it passes the US medical licensing exams. without cramming, as this headline says. But the question is, did it cram by having the huge pre-training set that allowed it to, in some sense, memorize some of the answers to these or similar questions? I wrote about this in a Substack post and asking, how do we know about data contamination? How do we know about shortcuts? How do we know about the possibility that these questions really, you can answer these questions, but don't have abilities to generalize? And in fact, I showed that some of the questions that ChatGPT had done quite well on, if you phrase them in slightly different ways, the system fails completely. It's really not very robust. And this group wrote another blog post about how these professional benchmarks are the wrong answer to the wrong question, in that human benchmarks are really meaningless for bots for many different reasons, some of which I've talked about. So now people are starting to really probe a lot of these large language models, giving them tasks that require sort of abstract thinking, abstract reasoning, analogical reasoning. And the results are really interesting. That sometimes they do quite well, but if you probe them, you find some interesting limitations in the robustness of the abstractions that they create. So for example, one of the really striking things about large language models was they, like clever Hans, they seem to be able to do arithmetic without having been trained on it. Here's a paper that showed that GPT-4, for example, was able to do extremely well on problems involving addition and subtraction and division, surprisingly not multiplication. But another paper looked into this and showed that for another similar language model for which the training data was public, unlike ChatGPT or GPT-4, it turns out that the arithmetic abilities correlate very well with how often the exact numbers involved in the problems were seen in the pre-training set. So for here, they show an example where 24 is much more frequent than 23 in the training set, and the system is able to deal with problems involving that number 24 much better than 23. And they showed that in a much more systematic way, which hints at a lack of an abstraction ability. It's not doing abstract reasoning for doing arithmetic, but relying on pattern matching with its training set. Another paper, a recent paper called Reasoning or Reciting, showed something similar. They looked at several different tasks in which GPT-4 in particular was pretty good on doing reasoning tasks. And then they developed what they called counterfactual versions of those tasks. That is variations of the tasks that if you had the underlying sort of abstraction, you would be able to easily adapt to. But GPT-4 was actually much worse, dramatically worse on these counterfactual tasks. So as one example, code execution, I'll show that here. GPT-4, if you give it a little snippet of code in Python, and ask it to execute it. So, here's a prompt. You're an expert programmer. Hold on. What is the following code snippet in Python 3.7? Print. And it did, over many code snippets, the accuracy was very high. But then the counterfactual task was, instead of having 0 indexing for lists and arrays, the version of Python had 1 indexing. So they said, here's a new programming language, which is identical to Python, except all the variables use 1-based indexing, et cetera, et cetera. What is the code snippet print? So presumably a human, given this, who is an expert programmer in Python, would be able to adapt their knowledge and reasoning abilities to this very similar variation on the task, and yet GPT-4 was not good at this adaptation. And another paper, there's kind of been a whole slew of similar papers. This one I like that they had the title Embers of Auto-Regression, which was kind of poking fun at the Microsoft paper Sparks of AGI, which you might have seen. But they showed that in many cases, if you have a task that's common in the training data, the pre-training data, the system is very good at it comparatively, versus a version of the task that's much rarer. So they looked at like shift cipher decoding, pig Latin encoding, acronyms, solving linear functions, and so on. And they looked at sort of the accuracy on things that were very much like what has been seen in the training data versus versions of the problem that were very rare, and showed that, you know, the decrease in accuracy was quite significant. So the take-home message from all this is that large language models seem to be better, often dramatically, on solving reasoning tasks that are similar to those seen in the training data, but not on those that are not seen in the training data. And that raises the question of whether they're actually performing abstract reasoning, or what you might call pattern matching with examples in their training data. All right, so obviously we could say, isn't that true for humans too? Aren't humans better on doing reasoning with familiar content rather than unfamiliar content? Are humans really that good at abstract reasoning? And I'd say, yeah, that this is true. Humans are much better at familiar content. But I believe, and I think, you know, it can be shown empirically that humans are much better at out of distribution, generalization, and abstraction than today's machines. So in short, evaluation of AI systems, intelligence, and understanding can be tricky. You know, to understand true capabilities, first of all, you need to know what's in the training data. The striking example of that was this student posted on Twitter that the easiest problem, one of the benchmarks that OpenAI had tested GPT-4 on was called Code Forces. It was a coding benchmark. And he pointed out that, you know, of the easiest problems, GPT-4 solved 10 out of 10 of them, of the ones that had been published pre-2021, and 0 out of 10 since then. Of course, 2021 was the training cutoff for GPT-4. And so this strongly points to data contamination, which OpenAI really hadn't discovered in their analysis of GPT-4's performance. So we really need to know what's in the training data. That's going to be hard for large language models built by commercial companies who don't want to reveal the training data, but more and more there are now beginning to be at least open source systems that not only open source the model, but also open source the training. And that's how we're going to be able to do science on these things. And to do science, we need to systematically test variations of tasks, like I showed you, not just single instances. That this may seem obvious, you know, this is people in psychology know this very well, but in AI, it seems often just showing performance of a AI system on a particular task without testing its robustness at all. That's quite common. And I think, you know, people are starting to test these systems adversarially, or if you like, counterfactually, like the example I showed you, where you specifically find examples that are far from what's been trained to assess the robustness or abstraction abilities of these systems. So in the last part of my talk, I want to talk about one example of this kind of testing that was proposed by Francois Chollet at Google in this really interesting paper from 2019, where he asked, what is a fair way to test intelligence in both humans and machines? Of course, intelligence, is another one of those words that is ill-defined, but Cholet defined it as the ability to efficiently learn new skills, essentially, and to abstract, by being able to take knowledge that you have learned and apply it to new situations. And to this end, he proposed what he called the abstraction and reasoning corpus, or ARC, which is a set of visual puzzles, grid-based puzzles, in which patterns in a grid are transformed. You're given a few demonstrations of a transformation and asked to apply, to infer the underlying rule and apply it to a new example. So it's an analogy problem, essentially. So you can see that, you can have any size or the grid of any dimensions. There's certain sets of colors that are available, and it's a non-linguistic task intentionally, because the language has there's a lot of issues with sort of memorization in language, as we've seen, that systems that are trained on language, they can have memorized a lot of their training data and do pattern matching to that. But here, this is a really test of basic spatial and semantic knowledge that has been referred to as core knowledge systems in developmental psychology by people like Elizabeth Spelke et al. So Cholet took this idea of core knowledge systems, which consists of knowledge that is possibly innate in humans, possibly learned very early on, having to do with objects. The world is divided into objects. Objects have certain properties and interactions. The world is spatial, and we understand things like inside and outside, on top of, on bottom of, around, surrounding, basic spatial and geometric notions. Knowledge of small numbers and numerosity, things like something is greater than something else, and so on. And in Spelke's papers, she also includes knowledge of agency, that some objects in the world have agency and goals, and others are, inanimate and don't have such agency. So if you take the top three, this is what the ARC domain's prior knowledge is meant to be. So this is what's expected. Here's another example of a task. So Cholet called these tasks. So you can see there's 3 demonstrations, and you have to infer the rule and apply it to the new test. And it's pretty easy to see here that there's certain kinds of shapes, and you color certain kinds of shapes red, certain kinds of shapes blue, certain kinds of shapes purple or pink. And it doesn't matter whether those shapes are rotated in a certain way or have a certain size. Their class of shape is invariant, and we can see that very easily because we have this kind of prior knowledge about shapes and about invariance. So Cholet created 1,000 tasks of this kind, and he published 800 of them and held out 200 as a hidden test set, and then put them up as a challenge on the Kaggle platform, which is a website for machine learning challenges, where you can actually earn money to submitting your programs. And so here it says 316 teams, eventually almost 1,000 teams submitted programs to this challenge. These programs were tested on the hidden test set, and the top winning program had about 20% accuracy. And accuracy, each program is allowed 3 guesses per task. And the ensemble of the top 2 programs got 31% accuracy. But the top programs what they did was they were essentially program synthesis approaches where the programmers defined a set of primitive grid operations like reflection, rotation, recoloring, a bunch of other primitives, and then tried to generate a pipeline of those primitives that would result in transforming the input to the output in the demonstrations, like these demonstrations, and seeing if that then worked on the test. And you can see they were not very general. So there's a new competition. You can earn 1,000 Swiss francs for every percentage point your program gets above the current world record. And that's going to end at the end of 2023. So I don't know what's going to happen there. But I got really interested in this ARC domain, but I thought it had a couple of problems with it. One was each task, it tested understanding of a certain kinds of concept like shape invariance, but there's no sort of systematic variations on that concept to try and test robustness of understanding. So, there was no systematic variations of, say, this problem. So if a system got this right, we couldn't really conclude that it had a robust understanding of shape and shape invariance. It might have gotten it right for some other reason. And also if you go through the benchmark, a lot of the tasks are actually quite difficult, even for people. And I think that is sort of limiting in how, making progress for AI systems. It's like it's too hard. So my collaborators and I at the Santa Fe Institute came up with a version of ARC called Concept ARC, which was meant to get at these problems, was meant to evaluate understanding and generalization in this domain. We have a paper that was recently published in Transactions on Machine Learning Research. And we tried to more systematically test understanding of core concepts in a way that would be quite easy for people. So we created new variations. We defined 16 different concepts, things like center, inside, outside, same versus different, top versus bottom, that got at these spatial and semantic, very basic concepts. And our variations had sort of systematic increase in complexity and degree of abstraction. So as an example, here's a task that in our domain, okay, so you can see 3 demonstrations, the test input. You can probably very quickly say, okay, remove the bottom object, whatever it is. And we tested that on the Kaggle winning program. We ran it on our problems. It got it correct. We also tested humans using the Prolific and Amazon Mechanical Turk platforms to get humans to do these tasks, and everybody got this right. And it's sort of, so now can we conclude that both humans and the Kaggle winning program understand the concept of like top and bottom? Well, no, we have to test further. And so here's another variation. Okay, so you can look at these demonstrations and you probably can easily see the rule is color the top row red. Everybody got that one right. But now here's another variation. Let you look at that for a minute. You can probably quickly see, as all humans did, that we're removing the top and bottom objects. But Kaggle winning program couldn't do that. It wasn't robust. Its understanding of top and bottom were not robust like humans. Here's another example on a different concept group. Let you look at that. And so here the answer is keep the objects that have the same shape. Okay, so everybody got that right. Another variation on that, we're keeping the objects that have the same shape, but we're ignoring and getting rid of the sort of outer coloring. Okay, everybody, all the humans got that right, but the Kaggle winning program got that incorrect. And finally, another one here, we're removing the objects that have the same outer color. Okay, again, most humans got that right. Kaggle winning program got it wrong. And we also tested GPT-4 on our tasks. Of course, GPT-4 at that time only had a text interface. You couldn't give it pictures. So we translated the grids into numbers representing colors. And this was, we basically copied a pattern of prompting that was used by another group who had written a paper on analogy using large language models. And they had this kind of prompt where they represented grids in this way. It was, in that case, GPT-3 and GPT-4 were able to reason about grids using these kinds of representations. So we tried the same thing. And we found that it did not do very well on this task. And in fact, here's all of our results. So for each concept group, here's the different groups of concepts. And within each of these, we had about 30 tasks that were variations on that concept. Here's the sort of average human performance on these. And, you know, human performance using these crowdsourcing platforms can be quite noisy, as many of you, I'm sure, have experienced. But overall, humans did very well on these. The Kaggle First Place program, it got way above the 20% accuracy that it had gotten on the Kaggle competition because we intentionally made our problems much easier, at least for humans, but it still was far below humans. And GPT-4 didn't do well at all, at least using the prompting that we gave it. So our current work on this is we're doing some additional tests of large language models using, for instance, what's called chain of thought prompting, which is maybe a friendlier way to show it what the task is. We're also testing new multimodal foundation models that involve vision and language so that we can show images. We're building a system inspired by human visual reasoning to solve these problems. And we're also looking at how humans and machines might use natural language to scaffold concept learning in this domain. So this was sort of an example of how to test understanding of very basic concepts in humans and machines. But I still have, you know, with respect to the debate over understanding in large language models, I want to conclude with the questions that David Krakauer and I posed in our paper in PNAS. We asked, is it true that talking of understanding in such systems is simply a category error, as Alison Gopnik argued, in which we're mistaking associations between language tokens, which is, you know, what these large language models form, for associations between the tokens and actual physical, social, or mental experience, which perhaps these systems don't have. Is that so? So that's one side of the debate. Another side is the opposite. Do these systems, or maybe their near-term successors, actually, even in the absence of physical experience, create something like the rich concept-based mental models that are central to human understanding? You know, something that in the context of this lecture series, you might call grounding. And if so, will scaling the models create ever better concepts? So, you know, there's proponents on both sides. There's proponents of number one and proponents of number two. And I think the evidence is not there yet for number two or number one. But we have a number three. If indeed, these systems don't create human-like concepts, causal, compressed models of the world. Could it be that their unimaginably large systems of statistical correlations actually produce abilities that are functionally equivalent to human understanding, that don't have the robustness problems that I mentioned during this talk, or that enable new understanding that humans are incapable of accessing? Should we allow this kind of large system of statistical correlations, which, you might call a shortcut in some examples, but in this case, maybe it's functionally equivalent to understanding? Is that a possibility? So I'd love to hear your thoughts and any questions and comments, and thanks for listening.
Thanks, Melanie. It usually takes a couple of minutes before people get courage to ask questions. So I usually perform that function. Are there any questions? If so, just raise your hand and I'll recognize you now. Okay, Lucian, go ahead.
Hi, thank you, Melanie, for a wonderful talk. I have a question with the machine training that you've read in the literature and you've done in your lab. How much training do you need? Suppose the pattern is very consistent. Do you need a lot of exemplars and a lot of repetitions, or just a few exemplars, a few repetitions, or hardly any repetition? Then they get it, like humans, relative to humans.
Are you talking about with the abstraction and reasoning corpus problems specifically, or some other, or more generally?
Like the experiments you presented at the end, for example, even the spatial stuff, like abstraction you've shown.
Right. So the whole point there is that it's few shot inference. You only have 2 or 3, or maybe at most 4 demonstrations, and you can think of those as the training examples. And we humans are relying on a lot of prior knowledge about space, about objects, about, relationships, spatial and semantic relationships. But the idea is that you can't rely on huge amounts of training data to solve these problems. Abstraction is all about few shot inference. That's the point. And so, I guess for this ARC domain, the point is not to have a big training set and a big test set that, you train and then you test. The point is to be able to do this few shot inference without any training specific to that corpus. You're training.
That's exactly what I was trying to see, because the final examples you had that you did with all the spatial things, those were, you had equivalent amount of demonstration exposure to the adults and to machines, right? And then you got those kind of, in some cases they had compatible. They're not very many times. You just present a few times, not many repetitions.
Exactly. Machines, the machines have not seen any more examples than the humans. Exactly.
That's wonderful. And so the machine potentially in certain tasks can perform as efficiently, as quickly as humans, but they fail or less good in both some other tasks.
So I mean, for the concepts that we tested, there were some concepts that the machines were much better at than other concepts for various reasons, some of which we don't know, but definitely they're far below humans in all of the concepts that we looked at.
I thought it's amazing that sometimes they are fast, they're good, but they're cheating, right? They're using other methods, some things that are irrelevant.
You want to call it cheating, right? Yeah, I mean, machine learning systems learn what there is to learn, like whatever cues they can use most efficiently, they will. So it's not hard to get machines to learn shortcuts if the shortcuts are there.
Stephen, can I raise another question, or should I wait to get other people? Another question is that in humans, there's a lot of studies on human abstraction based on exemplars. especially children who are not taught the rules, then of course it's quite easy for humans, even for children to generalize rules based on exemplars if the exemplars are consistent. But in a lot of cases, the exemplars are hardly consistent. Like those examples you gave for counter examples, those are not. And what humans can do, and even young babies, we've tested young babies, 1-year-old, they're able to tolerate certain amount of inconsistencies. So I'm wondering, those spatial tasks you've done, have you considered using some level of inconsistencies? Of course, even for humans, we know for adults and humans, for babies, you have certain, this is all predictive based on algorithm. If you add certain amount of certain threshold of inconsistencies, generalization will not be made, right?
Mm-hmm.
But let's say we take some basics that humans can, right? Can the machine handle those inconsistencies? I thought that would be very important for testing to show the level of generalizability.
You mean sort of give demonstrations that actually are wrong?
Like say 100% in your case. Let's say in 80% of exemplars, they've seen shots correct, 20% not right, up to 50% correct, 50. Then you can make predictions, and it has been shown in babies, in adults, that at some point, according to predictions of different theories, at some point they break the rule. Learning is no longer possible. Like language also, you just the past tense, you can learn it because most cases it's okay. But it's okay, you have cases right, wrote, run, wrong, because these are not very often. And so you don't have to memorize them. But in cases when the rules are no longer represented by most certain number of examples, so humans are able to track both. So I'm wondering if machines, that will maybe explain why they're trained with good exemplars, and then on the roadblock there's something different, then they crash into the street side, right? And so there's difference between adults and babies too. Adults will do probability matching. So meaning that it has to be good enough, but they also would make some mistakes if you have certain amount of inconsistencies. But with babies, babies, children, the younger they are, the more they will regularize, meaning that this is the force of language change over evolution. So I'm wondering, of course, machines, I would assume at best it can perform maybe like adults. They're not as smart as babies, but I wouldn't expect them to over regularize or regularize inconsistent input. But I wonder if they can find patterns, rules based on inconsistent input, which happens a lot in life. That's all. Sorry to take your time.
Yeah, no, that's an interesting idea that I haven't worked on at all, but thank you.
Thank you.
Before we take Gary's question, we have a question here in the live. Could you say your name loud?
I am Iris Martinez.
Iris, and can you hear Melanie from here?
Yeah.
Okay, go ahead.
Concerning the ARC test, I was just wondering if there's a possibility that the models can solve this task, are actually designed specifically to solve this task. So I was wondering what it can teach us, and if these models could be used in other contexts, or if they're just specifically built to solve this specific ARC task, but they would not do very well in other contexts, or they would not be able to reuse these concepts of, for example, above or below in contexts that are not these specific tasks.
Yeah, I mean, that's an important question. The ARC test is obviously a proxy for more general abilities, and you could certainly possibly build a system that would do well on ARC and not be able to generalize to other sort of non-ARC examples, but I think it would be hard to do that. I don't know for sure. So obviously, in AI, we obviously have to show that our systems aren't just specific to a given benchmark, that you have to go beyond that benchmark. And that's something that you would need to do if you were really proposing that a system understood sort of top, bottom, inside, outside, all of those things. So ARC is just sort of a beginning, an idealized domain for building systems that can try and make sense of these ideas in this small domain, and then you'd have to show that they can extend that more generally. So yeah, great question.
So yeah, like a baseline, but after that, what would be the next steps? Like if, for example, if a model can solve the art task like very well, so what would be the next steps to check that it's
Yeah, I mean, I think you'd have to make more realistic kinds of tests. You could also try and have some more physical world tests with robots, understanding these concepts. You know, interestingly, if you look at some of the text to image systems like DALL-E or Stable Diffusion, they're very good at generating images that correspond to a prompt, except if that prompt involves like spatial and compositional relationship concepts. So they're not that good at like a green box on top of a red cube on top of a, you know, something else. So they don't have that understanding, that basic core understanding of spatial and compositional language.
Okay, thank you. Gary. Microphone. Microphone, that's it.
Yep, sorry. I don't think it's clear yet if we even know what understanding means in humans, but I wonder what you think the possibility. Let's bring this back to what the seminar is about, that is grounding. So we've given them vision and language input, but what do you think the possibilities are for understanding for robots if we embed these systems in a robot that learns by interacting with the real world, like, you know, learning that when you let go of something it falls, which fascinates young kids for quite a while. So do you think we can get to a level of what we might call understanding by embodiment in a robot that interacts with the world?
Yeah, I mean, given that we don't have a definition of understanding that we all agree on, but yeah, I do. I think the big, you know, one big question is it just a matter of sort of tokenizing the world and predicting the next token in a multimodal system, and then suddenly understanding will emerge? Or do you need something else? Do you need some kind of core knowledge system, innate core knowledge system? Do you need some kind of other part of the architecture besides just this, you know, self-supervised learning paradigm? I don't know the answer. You know, my intuition would be that tokenizing the world and predicting the next token, even in a fully multimodal system, might not be enough. But I think it's an open question.
Yeah, I don't mean to just have GPT in a robot. I'm just thinking about learning by interaction, reinforcement learning, you know, in the same way that we learn, you know, would lead to something that we would call, I guess, intelligent. And I mean, if you gave it long-term memory, I think is obviously important, which a lot of these don't have at the moment. Do you think it would lead to something we might call conscious? Just to use the I word, I'll use the C word. You said innate.
Yeah, I'm not going to get into consciousness here, but you know, there's kind of a big debate over how important is the architecture, like, as you say, long-term memory, etc. How important is the learning algorithm? And right now, a lot of people in the large language model world would say it's all about the learning algorithm. You know, we have our transformer architecture, and all we have to do, as Alex Demakis said in the tweet I quoted, all we have to do is turn the world into tokens and predict the next token. Then suddenly this all will emerge. I don't think so, but I can't prove it's wrong. And I think that's going to be the empirical question that we're all going to be facing now with these multimodal systems.
Okay, Jean-Guy. Okay, turn on your microphone.
Thank you very much for this very motivating presentation. One aspect I find very interesting is passing from typical language generalization problems to iconic or images or figures generalization. My question is that why do you pass from the problem of generalization and abstraction, and suddenly when you're generalizing into some general forms, you call these concepts? They could be categorizations of icons into structures. When you use the word concept, instead of just a general or an abstraction, philosophers see that concepts are abstractions, but the concept has another property. You can work on from concepts that are generalizations of other concepts. You have a hierarchy of concepts. The images you gave there they could be said they are concept or categories, but understanding starts when you can really play on your concept themselves. Is there any research in that field that you have your blocks that are generalized in a certain form, but deeper understanding starts when you're capable of generalizing your own concepts and building things? And the other property that concepts would have, at least for some philosophers as Brandon, is that not only can you generalize, you can do some inferences. And understanding starts there when you, with your concepts and generalizations of concepts themselves, you start building relations between your concepts. And one of the important conditions of understanding is that you can have inferences from one concept to another one. And not only that, if you go a little farther down in the theory of concepts, is that your understanding is not just a generalization, it's the relation or the integration of these concepts into your larger knowledge. So the picture of working with these ACR icons is highly interesting, but I did not see examples of categories that are concepts of concepts or any relations of inferences. Is something done in your research on that field?
So I'm very interested in that idea, this idea of hierarchical concepts. I think, you point to a fact that understanding there's kind of a spectrum of understanding, or a spectrum of concepts, if you like, that starts with sort of very basic core concepts, and then you can then compose concepts, you can make concepts hierarchical, concepts of concepts, you can integrate concepts into a larger knowledge system. I think we're sort of starting at the very basic level and hopefully building up from there. But, one example that I would love to see it from your, the idea of a hierarchical concept is, so we had these sort of what we called concept groups, like sameness or top and bottom. So a system that could do a hierarchical conceptualization would be able to look at problems and kind of say, which kind of problem is this? Not just solving the problem itself, but categorizing the problem as a kind of concept. I don't have a system that can do that. I don't think any AI systems can do that very robustly, but I think it's obviously a very important part of human intelligence. I agree. But I think these things are on spectrum, and we're sort of starting at one end of the spectrum and trying to build up to this incredibly deep, rich understanding system that you talk about of integrating all of your knowledge.
Okay, thank you.
Thank you. Before we go to Steve Hansen, there are two questions from remotely. Félix Ingrand and Jean-Louis de Sales. Do you want to pose your question orally, or do you want me to read out your question, or do you not intend that?
Okay. I can read it. Sorry. Can you hear me? I am sorry.
Yes, Félix, you want to ask it? Go ahead.
Sure, sure. So you mentioned the Microsoft paper. In this paper, we present this example where we are stacking objects, like we are stacking like a book, and I think it's a computer, some eggs, and some a bottle and a nail. And basically, I don't think that this example was presented in the training set, but still ChatGPT-4, I mean, is able to stack properly the 5 objects, and it's. I mean, I think it's interesting to see that it looks like there is some kind of common sense of what is stackable, what is fragile. I mean, the eggs, if you want to stack them and put something on top, you have to put them into a square and things like that. So don't you think here that there is like some common sense of what is stackable and what is fragile, and what can be done when you are putting object together?
Yeah. So what you're referring to is this Sparks of AGI paper,
Exactly.
and one of the famous examples from it was they asked it, suppose I have a laptop computer, 9 eggs, other stuff. How would you stack them in a stable manner? And it came back with, well, I would sort of put the 9 eggs in a 3x3 array and put the laptop on top of that, because that distributes out the weight and so on. So yeah, that sure seems like physical common sense, physical understanding. But again, I think my point is that we don't know what's in the training set. We don't know if something very similar to that's in the training set. And how robust is that? And in fact, I wrote a blog post about this very example where I tried different versions of this stacking problem on GPT-4, and it did not show the same robustness at all on different versions. So the question is, how do we evaluate these systems? Just giving one example is not enough to conclude that it has robust human-like physical understanding.
Okay, thanks.
Okay, thank you. Jean-Louis also wants to ask it orally, but Steve was on first, so what I suggest is this: Steve, do one. You tend to have several. Do one question, and then I'll go to Jean-Louis, and I can come back to you for your follow-up. Okay.
So I have one question.
First.
Hi, Melanie. Great talk. I like the end of it better than the beginning in a certain way. I think in the beginning there's sort of 2 kinds of common errors that I've heard people talk about from the symbolic AI community about these very large deep learning transformers. The one is there's a little bit of cherry picking. So let's take Mr. Musk. I don't want to go through all your examples, but Mr. Musk specifically rejected deep learning vision systems and arrogantly developed one himself. And the first thing it did is went over and run somebody over. And then everybody said, oh, see, these things are interesting. Well, Waymo, on the other hand, has been out there for a year or 2, and it hasn't run anybody over as far as I know. And it's a deep learning vision system.
Steve, can you raise your volume? It's hard to understand.
Sorry.
You're talking very fast.
No?
And then talk a little slower and we'll understand better.
How do you know we're understanding, Stephen?
Thank you, Gary. Can you hear me now?
Yeah, I hear you, but it's hard to unscramble it. Maybe it's just me.
Okay, well, let me fix this and you can come back to me. How's that sound?
I can try and I can hear you okay, so I can try to repeat the question.
So let me continue. The second thing that I kind of error that's made in this context is a projection. It's sort of like the problem with the large language models, or let's just say the transformers, is we don't know what happened. Okay, something changed there, and then I'm going to use the E word. I think there's something emergent here. There was a tipping point at some point, and something happened inside of these things that produced some kind of fluid, context-free grammar and other kinds of reasoning. But I agree with you in general, especially in terms of your ARC kinds of problems, which I think are interesting. You should be aware that GPT-4 now has image input, just so you could actually do these experiments rather than binary vectors, which I think is a little unfair.
Yeah, that's what we're doing now.
Okay, and so those are the two. But the other thing is, I have ChatGPT here, and I just asked it about you. It knows you, but here's the more interesting part that it said. Well, I can attempt some forms of reasoning. The ARC tests are specifically designed to challenge the limitations of current machine learning architectures, including mine, which is interesting. Now, I don't know its pronoun, so it's an it. Okay, so we'll just go with that. So it says, these tests often require a level of abstraction and generalization that I might not be fully equipped to handle. Self-aware. For example, they may include tasks like pattern recognition in a more complex abstract form than what I'm trained for, or they may require logical reason based on sparse information. However, I'm happy to try if Melanie has the test right. So the interesting thing about ChatGPT here, and if you interact with it on a daily basis, it does give the illusion, as you say, this kind of illusion that it's conscious, aware, and it's familiar with a lot of the concepts that you're using. Now, how much of that is bootstrapping from your own, because it's training on me when I ask a question. So it literally has a learning going on. Now, because these prediction systems, with the attention heads, you got 4,000 of them, and you take like some covariance of this and you calculate a predicted output. This is incredibly stupid architecture. I'm sorry. I mean, I was doing this architecture back in the 80s, and of course I didn't have much data and I didn't have enough big enough computers. So the issue there about understanding, I think, is we're not ready for that question yet, because we don't really understand what these things are doing. And although I sympathize with, humans worrying about this, not so much about what Jeff Hinton's worrying about, taking over civilization, but something along the lines of misunderstanding what's going on here. The debates are going to go back and forth randomly until we get a better look at the visualization inside of this. Now, people have done some visualization in the context of Ula's work, and who was, I think, at OpenAI for a little while, and you see 50 to 100 million cluster contexts in this space that you can pull out. And so what really becomes interesting is how this thing navigates between these cluster contexts, and then how it produces an output, because it has no training for that. There's no training for any of the emergent things we're seeing. It's trained on large data sets from the internet, but if I sat around and read the internet all day, I'd talk like Gary. It just wouldn't make any sense. So that's a real problem.
Okay, that sounds like a question. Go ahead.
Wait, what was the question?
Oh.
The question was, at the end of this, how are, the problem is not the assessment of GPT. We've created something that's almost as complex as us in this context. And so it's really hard not to first understand what GPT is doing, how it actually, the internals work, and then to tease apart some of that. And we've had some speakers in this series who have done a little of that. Ellie Pavlink, in particular, had done some very nice visualization and testing where she could trace what the heads were doing, and she found there were sort of symbolic structures appearing inside of ChatGPT, but no training data for that. And so the whole business about training data and memorization, psychologically, I am a psychologist, that doesn't scan. It doesn't make any sense. I mean, we learn things, and yes, we memorize them, but, in implicit and explicit way somewhere in the medial temporal lobe, and it's certainly not stored in any database. So there's a problem with these computer analogies going back to human.
Is that a question, Melanie?
Well, it's more of a, I suppose, a hyperbolic rant, I suppose.
Yeah.
You know,
I mean,
I've noticed that there are people that have symptoms of having interacted with ChatGPT in excess. I've got them, you've got them. They ask different kinds of questions. But anyway, Melanie, can you do something with that?
I mean, I think you raised a lot of interesting points, including the sort of need for transparency on these systems so that we can actually try and figure out how they work. So all the work that people have done on this so-called mechanistic interpretability, like Chris Olah and Eli Pavlik, are using systems in which they have the access to the model, and often they have access to the training data. So we can't. It's really hard to do science like that on closed models. So I'm a big proponent for transparency. You brought up a lot, you know, I think some people will say we can't talk about understanding in these models unless we understand, as you say, how they work on the inside. And maybe that's true, but you know, we don't understand our own understanding very well. And we just use behavioral evidence for understanding in other people and sometimes in animals. And you know, it may be that for a while, at least, that's the best we can do with these large language models too. Because
well, just a comment.
Hold it, you'll get your chance. You'll get your chance. I just have to.
Done. This just is a throwback to behaviorism, and this is the other thing that's emerging in here is we're seeing B.F. Skinner kind of rise up in this story, and it's not a good look for trying to understand what understanding is. So,
okay. Hold that thought. Now we're going to move to Jean-Louis Dessalles, who has had something to say about the transition from non-language to language in the past. Go ahead, Jean-Louis.
Okay, thank you very much, and thank you, Melanie, for this impressive talk. I learned a lot. I hope you can hear me.
Yeah.
Yes.
Okay. Yes. Okay, my question is about inconsistencies. So it seems to me that it's a basic component of understanding. If we know that, for instance, the student doesn't understand when she didn't see the problem. So if a student is blind to some kind of inconsistency, we are sure that there was some kind of lack of understanding. Can we do the same with these language models? Are you planning, or have you already tested for the ability to detect inconsistencies? For instance, the fact that if I am in New York and then I have a call from a friend in Paris, and then she enters the room where I am, so there is an inconsistency because she cannot instantaneously fly from Paris to New York, for instance. So the world is, the human interactions are full of inconsistencies because it's a basic, when you are telling a story, for instance, there is a point, and the point is quite often around an inconsistency. Otherwise, there is nothing to tell. So that's the core of at the core of human intelligence. There is the sensitivity to inconsistencies. So, are you planning to test this? Have you already done this?
But not me personally. I mean, you're kind of getting at a notion of common sense. You know, we have this common sense knowledge, inconsistencies in our knowledge in things that go against our knowledge of the world. You know, people do experiments with babies and show sort of expectation violation experiments, and that's kind of a spot. So even babies can spot inconsistencies, right?
By the way, that's exactly what Rushen Shi, who gave you the first question, works on.
Yeah, right. So I think people have been trying to develop benchmarks or, you know, tests for AI systems that capture this ability to spot inconsistencies, but the benchmarks often have problems. So there's common sense reasoning benchmarks. There's even, you know, there was a effort funded by DARPA on baby common sense in machines, sort of that, the sort of being able to do that expectation violation detection in machines. But, you know, these things, the evaluations are flawed in many ways. So I think I agree with you, it's a very important problem, but the question is, how do you test it in a sort of way that will really give insight?
Thank you. Now we have 6 minutes for you, Steve. Go ahead.
Well, let me give 2 of my minutes to Gary.
I don't have another.
You've run out of questions? Okay, I figured. Yeah, so let me go back to the beginning of what I was saying, Melanie. So there's a particular person out there, I hate to mention his name because it gives him a little bit more attention than he should get because he's got so much, as Gary Marcus.
Don't mention his name.
And Gary Marcus, I'll mention his name again. Gary Marcus has who's been inconsistent and has also contradicted himself within a period of 4 months between this'll never work and now it's too dangerous because it makes mistakes, but it works. Okay, so he's holding on for this idea that, and I think many people are, that there should be some kind of symbolic connectionist neural network kind of merger. Is that what you're thinking of?
No, not exactly. I mean, I've seen a lot of, you know, there's this whole area now called neurosymbolic AI, and it encompasses a lot of different approaches, and some of them are interesting.
Yeah.
Seems like it's not an easy problem. It's not just gluing on a symbolic system to a neural network. Clearly, people have been trying to do that kind of thing forever, and it hasn't been very successful. So I'm, you know, I obviously, you know, we don't have our, whatever symbolic processing we do emerges out of neural processing. So if we want to understand our own symbolic processing, we have to figure out how that emerges. And I think that's something that is the right approach in AI too, is to figure out how to get non-symbolic systems to produce symbolic behavior. I mean, there was a paper from DeepMind, I can't remember who was the author, but it was about sort of contrasting symbolic processing with symbolic behavior. So the notion that we behave as though we're symbol processors, even though inside mechanistically we're doing sub-symbolic or some kind of neural processing. And that's maybe the right way to think about it, as an emergent property. But I don't object to people trying to do that kind of merger between these systems. It might, and I think, you know, people have, obviously, and Gary, even if you disagree with him, he has pointed out that a lot of the most successful AI systems that do real things are such mergers. So for instance, AlphaGo was a merge system between a neural network and a symbolic tree search algorithm. And most self-driving cars use both neural processing and symbolic rule following. So if you're trying to engineer something in the real world, maybe that's going to be an important part of it. But if you're actually trying to understand intelligence and cognition in biological systems, I think you do have to think about how the symbolic like behavior does emerge.
Right, I agree. I mean, one of the arguments people make sometimes is, so in human learning, there's 2 actual memory systems, maybe 3 or 4 actually, but the 2 are implicit and explicit, usually called procedural declarative in certain contexts. But the explicit memory system looks more like a rule-based system. And it could, in fact, it's the kind of thing we use a lot to tell us that, oh, don't step on the brake now, don't do this. And it's sort of, we're talking here. So the implicit system is all basically much closer to the neural networks, and it's not verbalizable. We just know how to do, if I say make some risotto, you go make it, right? If you've done it 100 times, you don't need to look at the recipe. So there's a sense in which this embedded information that's inside it, but there does it that this interface, which wasn't trained, which produces almost perfect grammatical output, not always correct. But then I have friends who say things like Gary that are not always correct either, but he speaks perfect English. So this is confusing when people pick on this system, when in fact, this is part of the fault of the training data, probably more than anything else.
Guess we'll see.
Okay,
Within a few minutes ahead.
looks like we're coming to closure. We're almost done. And I want to just say that next week's going to be a somewhat different speaker. It's on the same theme, but Dor Abramson at Berkeley works on bodily, the question was raised several times today, bodily ways of conveying to students mathematical concepts, including spatial concepts and more abstract concepts. So I invite you to come next week for that. Thank you for coming. I want to especially thank Melanie. It was a wonderful talk. We had good discussion, and I hope you'll be coming again sometime soon.
Yeah, thanks so much for inviting me. Really had a great time. Thanks.